So one type of problem that we do in related rates is the conical tank problem, which goes like this. Water pours into a conical tank of height 10 meters and radius 4 meters at a rate of 6 cubic meters per minute. At what rate is the water level rising when the level is 5 meters high? So what we want to do is draw a picture of this tank. Let's just put it up here. This is the conical tank, and draw a circle like that. So a cone, it has a circular base. I know I haven't really drawn it symmetrically. Let's put the axis a little closer to the center. I have to make it slightly off kilter. But this is a cone, and the cone itself is 10 meters high, and the radius of the base is 4 meters. So that's 4 meters, and that's 10 meters. So the question is, at what rate is the water level rising when the level is 5 meters high? What you have to realize is that since the cone is skinny at the bottom and wide at the top, what that means is that if I'm adding a constant rate of water into this cone, the water level is going to rise very, very fast when we pour it just into this point, but it's going to start rising slower as it goes upward. So the thing that also you have to realize geometrically is that what's going on is, oops, try to make that blue for water, is what I'm asking about is how fast this water level is rising, and you have to realize that the water that is underneath the level is actually a smaller cone. So we're not really asking anything about the rate at which the big cone itself is changing, because it's not. It's a constant, it's a constant size cone. What we're asking about really is how fast the dimensions of this smaller cone that actually has the water in it, is changing. So all right. So what we want to do is let's first start by assigning the variables. Um, we can say most people will look at this and they'll say, sure, one of the variables is v for volume, but that what that does is it does this part of the sentence, assign variables, without doing the most important part of the sentence, which is very precisely volume of what. And you can say volume of the cone, but which cone? If we're talking about the green cone, that just has a constant volume determined by the formula v equals 1/3 pi r squared h, with r equal to 4 and h equal to 10. So we're interested really in the volume of this small cone, the one that actually contains the water, whose top is that blue wavy line. So it's the volume. It's really the volume of water in the cone, which itself is this smaller blue cone down here. And of course, that's going to be measured in something, and it's going to be measured in cubic meters. So that's V. We can also see that that we should have an h variable, which looks like height. But again, height of what? Is it the height of the big cone? Is it just a constant of 10 meters? No. You don't ever assign a variable for something that cannot change. The height of this cone is 10 meters. It doesn't change. It doesn't get a variable. What we're talking about instead is the height here, the height of the water. The height of the water in meters. And let's see. So we can also talk about the radius. That's a useful thing to do. But of course, if we're talking about that radius, not the constant radius of the top of the cone, but the radius of the smaller blue cone as the water fills up. That's the thing that can actually change. So r is the radius of the small cone that has water, and that's in meters. And finally, we need t. T is time. But again, time what? Time since the universe began, time since 1900, since the year 1900. No, we mean time in minutes. Why did I choose minutes? Because the problem gives us minutes since filling began. So that's what t is. There are our variables. Okay, so what rate is the problem looking for? It says, at what rate is the water level rising when the level is 5 meters high? So what we're asking about is at what rate the height of the top of the blue cone is changing. And we're asking how fast h is changing with respect to changes in time. So the answer here is going to be dh over dt. So let's find one or more equations that relate the variables. What we know is that the volume of water in the cone, since this blue cone is just a smaller cone, we know that the volume of water in that blue region is going to be 1/3 pi r squared h. How do you know that? You know that because you took pre-calc and algebra and geometry, and at some point during there was they gave you the equation for the volume of a cone with a circular base. And as we all know, zero is defined as the precise definition of the word zero is the total number of things that you ever learned in a math class that you're ever allowed to forget. So if you're asking, do you need to know what the volume of a cone is? Yes, you do need to know the formula for the volume of a cone. So anyway, so what we know is that an equation that relates the variables is v. I can write it in red. V equals 1/3 pi r squared h. The thing is, I really want this in terms of one variable. If you notice, the variable, the quantity that we're being asked about is dH over dt. It doesn't really involve r. So what I really want to be able to do is I want to be able to write this entire equation just in terms of h. That involves a little geometry, which I'm just going to do over here. Notice, let's put this in red. Take a look at this triangle and this one. So let's see, I'm going to write it this way. The big triangle, I'll use two different colors here. There we go. So the big triangle has a height of 10 and a radius of 4. I know I haven't drawn this anything like in proportion. The small triangle has a height of h and a radius of r. But these triangles are similar to each other. Why? Because they both have a right angle here. They share this common angle, or so rather, these angles are by a theorem having to do with transversals that you should remember from geometry. These angles are congruent to each other, and then they share this angle. So these triangles are similar, and what that means is that 10 over 4 is equal to h over r. So what that means is I should be able to write r in terms of h simply by cross multiplying and getting 10r equals 4h. So r is equal to 4 over 10h, which can be written a little more succinctly as 2/5 h. So r is just 2/5 h because as the cone fills up with this blue wavy line, the radius grows in proportion to the height. As the height grows, the radius grows in a specific proportion to that. Point being that we just solved algebraically that r is equal to 2/5 h. So let's actually rewrite the volume in terms of just h. That's going to be 1/3 pi times the radius is 2/5 h, so that's just going to be 2/5 h squared times h. And that equals, the volume is equal to 1/3 pi times 4 over 25, h squared times h is h cubed. That actually equals 4 pi over 75 h cubed. So there's a good equation. V equals 4 pi over 75, not h down there, h cubed. And the other thing that's given in the problem is we're told that the water is pouring in at a rate of 6 cubic meters per minute. So what that means is that the volume of water in the cone is changing at a rate of 6. Well, we know that change in volume, what we're given is change in volume per change in time. You can kind of read that here just right off the units given in the problem. Meters cubed is a unit of volume, minutes is a unit of time. So this is like volume per time. And we can conclude that we're being given that dV over dt is equal to 6. So these are our two equations that we're actually going to make use of. Now what we want to do is differentiate. We want to differentiate with respect to time. So dV over dt is equal to 4 pi over 75 times the derivative of h cubed is going to be 3h squared. But, since we have is sort of like h cubed, it's like h is the inner function and cubed is the outer function. What we need to do is we're going to have to then multiply by the derivative of the inner function. We're differentiating with respect to t, so that's going to be dH over dt. That's the chain rule step there. Now, if this doesn't entirely make sense to you, just understand that in most related rates problems, what we're doing is we're taking an ordinary derivative of whatever variable there is, and then at the end, we multiply by d, that variable, over dt. I think that as you do this more, it will become apparent what the meaning is, but if you never really understand it, you'll still be able you really can't go wrong when you're asking for a rate with respect to time. You really can't go wrong by just taking an ordinary derivative. Now, if I had said find the derivative of if I said v is equal to h cubed and I said find the derivative of v, you'd say, oh, v prime is equal to 3h squared, but then just multiply it by dh over dt. I think eventually you'll understand why you're doing that, but if you before you understand it, you really can't go wrong by doing that. So that's all I did here. To clean this up a little bit, this is going to be 4 pi over 25 times h squared times dh over dt. Okay, so now I want to use the derivative in step 4 to solve the problem. Recall that what I'm being asked for in the problem is the rate at which the height of the water is changing. In other words, dH over dt. So since this is the equation that I have, is dV over dt equals this. In other words, is equal to 4 pi over 25 h squared dH over dt. That means that I can solve for dH over dt just by dividing both sides of the equation by that quantity. So it looks like I've got a reciprocal there. That's going to be 25 over 4 pi h squared times, I still have to, in other words, I'm still multiplying this with the reciprocal of this by what appears on the left side of the equal sign. So dV over dt is equal to dH over dt. So I now really have an equation that I can basically just plug in everything that I need. The problem tells me that the water level is 5 meters. This is when we care about what the rate is. We care about finding the rate when the water level is 5 meters, and we're told that dV over dt is 6. So I just plug in those values. H is 5, dV over dt is 6, and I get that dH over dt is equal to 25 over 4 pi times h is 5, so 5 squared, which conveniently comes out to 25, and then dV over dt is 6. So in other words, this is h, this is the given dV over dt. This comes out now to 6 over 4 pi, which I've done the calculation. That comes out to approximately 0.477, the correct unit, since we're asking how fast the height is changing. Height is measured in meters. The unit of time is minutes, and that's the answer. And usually I try to zoom out and show you the whole problem, but these problems are so long that it just won't fit on the page. So I'll just put up the original problem here, and you can go back and forth in the recording and see what parts of the problem you want to look at.